Hello, this is Dr. Dominic White from George Mason University. In this video, I want to recap the basics of statistical inference. First, what do we mean by statistical inference? Remember that the world around us is fundamentally a random place. If I repeat the same experiment twice, I will most likely get different results each time. How can I make sense of the processes that govern our world when all the data we collect contains such random variation? For example, if I give half my patients a new drug and the other half a placebo, how can I know whether it was the drug that improved their outcomes versus just random chance? Recall our previous example of differences in promotion rates between men and women. In this real example, a resume was sent out to a group of bank supervisors. The only difference was whether the name on the resume was male or female. The resumes with male names were more likely to be seen as worthy of a promotion, and there was a large difference in proportions, about 30% between men and women. However, in a fundamentally random world, this 30% difference could have arisen by chance. Even if there was no systematic bias against women, no two people would agree. We could see that some reviewers didn't think that the male resume deserved promoting, for example. So how can we tell how likely it would be to get such a result through sheer chance? Well, that's where statistical inference can help us. As scientists, remember that our first step is to come up with a hypothesis. This is because what distinguishes science is that it can be shown to be wrong. If instead we collect the data first, and then try to fit a plausible story to it, we are never leaving our ideas open to being shown to be wrong. Remember also that we need both a null hypothesis and an alternative hypothesis. The null hypothesis always says that there is no difference, that a drug has no effect compared to a placebo, or that gender has no effect on promotion decisions. The alternative hypothesis is usually what we actually care about, the result that we hope to find, that there is some effect. Why is the null hypothesis that there is no difference? Why do we even need a null hypothesis if what we actually care about is the alternative hypothesis? Well, we need a null hypothesis of no difference because we can calculate the probability of different outcomes in such a world. For example, we can simulate what the difference in fractions of 48 promoted men and women would be in such a world where gender had no effect on promotion. We can shuffle up the original data 10,000 times. We call these random shuffles permutations. So we permute the data 10,000 times, each of which imitates a universe in which there is no effect of gender on promotion. Unsurprisingly, this distribution would be centered around 0, i.e., no difference between the genders. But there would be some of these random universes, i.e. some of these simulations, where either more men or more women would be promoted. So that's our null distribution. Then we take our actual real difference in proportions, which if you remember was 0.3 or 30%. We call this value of 0.3 the observed statistic. And then we see how much of the null distribution is more extreme than this observed statistic. In this picture, you can see that the observed statistic is the vertical red line, which is plotted at 0.3, and the proportion of the null distribution permutations which were more extreme than this, you can see shaded in pink. This shaded pink area is also known as the p-value, the probability of getting a value of the test statistic in the permutations as or more extreme as the observed statistic from the real sample. For example, if we do 10,000 permutations, then the fraction of the more extreme is the p-value. If 100 are more extreme, in other words, if there are 100 simulations in the shaded pink region, then the p-value is 100 divided by 10,000, or 0.01, or 1%. It's important to remember two things about p-values. 1. The p-value is the probability of seeing a particular value of the observed statistic, assuming that the null hypothesis is true. That's very important. We assume that the null hypothesis is true, and calculate its distribution as you see here. The p-value tells us nothing about whether the null hypothesis itself is actually true or not, or the alternative hypothesis. We've had to assume that to calculate the p-value in the first place. The second thing to remember is that it is just a probability. Let's say we calculate a 10% chance or a 1% chance that a piece of data could have come from the null distribution. How do we decide whether that is unlikely enough to be surprising? Is 10% unlikely enough? Is 1% unlikely enough? What statisticians decided many years ago is to compare the p-value to a threshold. This threshold is called alpha, and its value is 5%, or 0.05 if we were to write 5% as a probability. So what we are saying is, if the data, the observed statistic, is so extreme that there is less than a 5% chance that it actually came from the null distribution, well, then we are reasonably comfortable saying that it is extreme, that it's unlikely. In that scenario, we reject the null hypothesis. Remember that we have calculated the probability of the data, not the hypothesis. So we cannot say that we have disproven the null hypothesis, only that we reject it in this experiment for this one piece of data. If this has made sense, you should now be starting to question whether p-values are particularly useful. In fact, a single p-value does not tell us very much at all, especially if it is only just below the alpha value of 0.05. What we really need to do as scientists is to repeat an experiment many times. If we keep on getting a small p-value, experiment after experiment, and repeatedly rejecting the null hypothesis, then we might start to believe that we have discovered something meaningful.